students, welcome to Sunil's tutorial. I'm Sunil Milwani and today we'll be doing this chapter called as thermodynamics. Now last lecture we were seeing solute-solvent interaction. Now let us see, why does solute-solvent interaction take place? Let's try to understand what do we mean by enthalpy of hydration. Suppose if I take a gas in ionic form, say this is my gas which is in ionic form, and if I react this with X moles of water, right? So in that case, what will happen? The ion would dissolve in the gas to give you MH2O X to the base X M plus, right? And this amount of energy required to react a gaseous mode with water is called as enthalpy of hydration. What is enthalpy of hydration? It is the amount of energy required at constant pressure for a gaseous mode to react with water. Simple. Fine, do we understand this? So what do we understand by enthalpy of hydration? Enthalpy of hydration is the enthalpy change involved in the hydration of 1 mole of gaseous ion, right? Now due to hydration, why would I want to do hydration? Due to hydration, what will happen is that the ion would get stabilized, the water molecule surrounding the ion produces a shielding effect. Now if you all remember what is shielding effect, guys, it produces a shielding effect and thus decreases the attraction of the ion. Now in 11th standard we have learned this, that suppose if this is my nucleus, this is the electron, this is my electron in the second orbit, say this is my electron in the third orbit, then the electron in the third orbit is attracted towards the nucleus, right? So it should straight move towards the nucleus, but as it tries moving towards the nucleus, it comes in close contact with the electron of the second orbit, and as we know that like charges repel each other, so the electrons in the inner orbit repel the electron of the outermost orbit, and this effect is called as shielding effect. Fine, so do we understand what is shielding effect? So because of hydration, there is a shielding effect that is created on the ion. Because of hydration, there is a shielding effect that is created on the ion which stabilizes the gaseous ion. Do we understand this? Right, let's write this down. Due to hydration, ions get stabilized. Water molecule surrounding the ion produces shielding effect. I hope everyone is able to recall what is shielding effect. It's the force of repulsion exerted on the electrons in the outer orbit from the electrons in the inner orbit, right? So that's the shielding effect. Thus decreases the attraction between the ions. So that is what hydration does. It stabilizes the gaseous ion, and the ion gets right. Now here I could say that the enthalpy of the solution suppose if I say enthalpy of the solution is nothing but it is based on enthalpy of crystal lattice and enthalpy of hydration. That's my enthalpy of the solution.
So what is that enthalpy of?
Crystal lattice. I'll explain to you what is enthalpy of crystal lattice, right? So that is your enthalpy of the solution. So enthalpy of the solution, that's how you use enthalpy of hydration, right? So enthalpy of solution is nothing but enthalpy of crystal lattice and enthalpy of hydration. Fine, do we get this thing clear? Now let's come to enthalpy of crystal lattice. Now what do I understand by enthalpy of crystal lattice? The enthalpy change accompanying the formation of 1 mole of a formula unit in crystalline solid is called as enthalpy of crystal lattice. Meaning, suppose if I have, say, if I have a molecule in gaseous state, right? Suppose if I have gaseous molecule M plus gas, I react this with some other element which is in gaseous state to get a molecule which is in solid state, right? So I would get certain enthalpy which in this case is negative. That is called as enthalpy of crystal lattice. To convert, to react the gaseous mole, okay, gaseous ion with another gaseous ion to form a molecule which will be in solid state, which will be in crystal lattice state. The amount of heat energy that is going to be evolved or absorbed in this case is called as enthalpy of crystal lattice. Fine, do we get this in clear? Right? So let's just write this down. What is enthalpy of crystal lattice? The enthalpy change accompanying the formation of 1 mole of formula units, 1 mole of formula units of a crystalline solid, 1 mole of formula units of a crystalline solid from its constituent ions, is called ions which are in gaseous state, is called enthalpy of crystal lattice. Fine, do we get this in clear? Now I could also have a reverse process for this, in which case I would have a crystal lattice. I can say that the reverse process, that is the separation of crystals into ions, is the reverse process, that is separation of crystal into ions is going to be nothing but I have the crystal which can be then separated into ions to give you M plus gaseous plus X minus gaseous, right? In which case here delta H will be positive. Fine, do we get this in clear? Now the reverse process of enthalpy of crystal lattice is the first step in the formation of solution. This is the first step in the formation of solution. When you want to form solution, you have to have reverse of crystal lattice. Crystal lattice enthalpy cannot be experimentally determined, but it is calculated by using Hess's law. Crystal lattice enthalpy cannot be experimentally determined. Cannot be experimentally determined, but can be calculated. By using Hess's law. Can be calculated by using Hess's law, right? To a series of reaction, obviously. Series of reaction. If I apply Hess's law to a series of reaction, I would end up getting the enthalpy of crystal lattice, which, right? So you cannot experimentally calculate it. It is done with the help of Hess's law. Now, if I am going to calculate enthalpy of crystal lattice by using Hess's law, then I need to start with elements in their standard state and end with ionic form. Because see this, guys, can you just see this equation? I have to start with elements in their standard state and I have to end in ionic compound in its standard state. Now the sequence of reactions which would enable me to get this are called as Born-Haber process, because this was discovered by two scientists. It's named after two scientists, Max Born and Fritz Haber, right? So I can say can be determined, can be calculated by using Hess's law to a series of reactions starting with elements in their standard state and ending with ionic compound, ending with ionic compound in its standard state. Right? This sequence of reaction is called, this sequence of reaction is called as Born-Haber cycle, right? It is named after Max Born and Fritz Haber. You need these names in your CET, right? So do we get this thing here? So that was that enthalpy of crystal lattice that we were talking about when we were doing enthalpy of hydration. Next, what do we understand by enthalpy of dilution? What is enthalpy of dilution? Enthalpy of dilution, it is the changes that occur in the solution when one concentration is diluted to form a solution of another concentration. So if I change a solution from a particular concentration to another concentration, then the enthalpy changes that would take place is called as enthalpy of dilution. Very simple. It is the enthalpy change that occurs when a solution when a solution of one concentration is diluted to form the solution of another concentration. That is called as enthalpy of dilution, right? Okay, I have already explained to you what is thermochemistry. It is the study that includes the study of enthalpy changes in a chemical reaction. Next, what do I understand by heat of reaction? What do we understand by enthalpy of chemical reaction? Which is also referred to as heat of reaction. Right. Enthalpy of chemical reaction. The total enthalpy change that takes place in a reaction. For example, consider for a reaction. If I consider a reaction, say, let's consider that I have A times A plus B times B gets converted into C times C plus D times D, right? Then in that case, what do I understand by enthalpy of a chemical reaction? Enthalpy of a chemical reaction is the amount of enthalpy change that takes place of the product to the amount of enthalpy change that takes place to the reactant. So C times HC plus D times HD. That's my enthalpy change taking place for the product. There are C number of moles of HC. 1 mole will take enthalpy of HC minus A times HA plus B times HB. That is my enthalpy of your reaction, chemical reaction, which is also referred to as heat of reaction, where I could say that where HA, HB, HC and HD are enthalpies of ABCD. Right? So in short, I could say that the heat of reaction is nothing but the sum of M times the enthalpy of the product minus sum of N times the enthalpy of the reactants. Right? Where I could say M and N are the coefficients of products and reactants, where M and N are coefficient of product and reactant, are coefficient of product and reactants in balanced equation. So in simple language, what do I understand by enthalpy of chemical reaction? The total enthalpy change of the product minus the enthalpy change of the reactant, right? The total enthalpy change, the change in the heat energy that occurs in the reaction product on the at constant pressure to the total change that occurs on the reactant side at constant pressure. Fine, do we get this thing here? So I could say that enthalpy changes change accompanying the chemical reaction enthalpy change accompanying the chemical reaction at constant temperature and pressure at constant temperature and pressure is called heat of reaction. Right? So whatever is the heat change that occurs, right? How would I define this? Definition, how would I define heat of reaction? It is the difference between the enthalpies of the product and the reactant, between the enthalpies of products and reactants with every substance in a definite physical state, with every substance in definite physical state, with every substance in definite physical state, and in the amounts represented by the coefficient, and in the amounts, that means how many moles I'm taking, represented definite physical state, and in the amounts represented by the coefficients, in the balanced equation. Fine. So do you understand what is enthalpy? We've already written the equation for this, right? So that is called as enthalpy of chemical reaction, or it is also referred to as heat of reaction, right? Next, what do I understand by, yes, you want to ask me something? Next, what do I understand by standard enthalpy of chemical reaction? Generally, when you are doing Hess's law, you will be writing your enthalpy in terms of standard enthalpy, which is represented as delta H degree, right? So, what do I understand by standard enthalpy of chemical reaction? It is the standard state of a substance to form in the form in which it is the most stable at a pressure of 1 atmosphere at a particular temperature, right? So when you try to measure the heat energy of a substance in its most stable form, right, under conditions of NTP or STP, then that is called as standard enthalpy of chemical reaction. So when you are doing any thermochemical reaction, including the ones which are for Hess's law, you will write your enthalpy as standard enthalpy. And do you get this thing here? So I can say that the standard state, it's basically when you measure enthalpy at STP or NTP, that is your standard enthalpy, right? The standard state of a substance, the standard state of a substance in the form in which it is most stable at the pressure, in the form in which it is most stable at a pressure of 1 bar. I hope you all know what is 1 bar. 1 bar is nothing but 10 to the power of 5 pascals, right? Or if you want exactly, it is also equal to, if you want the conversion factor in terms of atmosphere, 0.987 atmosphere to be precise, right? And at a particular temperature of 298 Kelvin, right? So if I try to find out how much is the heat in a substance when it is in the most stable form, and if I subject the substance to a pressure of 1 bar and a temperature of 298, then that is called as standard enthalpy of chemical reaction. Fine, do we get this thing here? Next, what do we understand by heat of formation? You will need all of this in your Hess's law. Standard enthalpy of formation. Standard enthalpy of formation. Right? It is represented as, it's also called as standard heat of formation. Heat of formation. And when you are doing numericals, they directly call it, instead of calling it as standard heat of formation, they may even call it as heat of formation, and it is represented as this. This is your representation for it, right? Now, what do you mean by heat of formation? Suppose if I have two substances and they combine together to form one molecule. Suppose, let's assume if I have 1 mole of a pure compound which is formed from its constituent elements. For example, if I take hydrogen gas and if I take oxygen gas to form water molecule, I would need half a mole of oxygen gas. Then the heat change that would accompany this would be called as heat of formation. So what is heat of formation or standard enthalpy of formation? It is the heat change that occurs a reaction in the formation of a compound from its constituent elements, right? Say if I get here, this will be called as heat of formation, and that's minus 286.8 kilojoules, right? Or it can be called as kilojoules per mole. So do you understand what is heat of formation? Formation of a pure compound from its constituent elements is heat of formation, right? So let's write this down. The enthalpy changes accompanying the reaction when 1 mole of pure compound in its standard state is formed from its element. In their standard state. That is called as heat of formation or standard enthalpy of formation, right? The reason why we are doing this is because when we do Hess's law, you shouldn't be very confused as to suddenly what is this heat of formation and heat of combustion. You should exactly know what they mean, right? Now, so in that case, I could say that suppose if I have to show it in the form of a general equation, then I can say that consider a reaction. Suppose if I have A times A plus B times B, which gives you C times C plus D times D, right? Now in that case, what will be my heat of formation here? Heat of formation is a form of heat of reaction. That means it should be enthalpy, sum of the enthalpy of the product minus the sum of enthalpy of the reactants. That means this should be equal to product. Product is C times C and D times D. So in that case, I can therefore say that heat of formation in its standard form, or heat of reaction in its standard form, that is, I'm going to be making 1 mole of the product, is nothing but C times enthalpy change of element C plus D times enthalpy change of element D minus A times enthalpy change of element A plus B times enthalpy change
So that
of
should be
element B.
capital D.
Which one?
Um, the top one.
You're considering element G. Right? So that is going to be your heat of formation in general form. Right? Next, what do we understand by heat standard enthalpy of combustion? Standard enthalpy of combustion is also called as heat of combustion. Now, represented as delta CH degree. Heat of combustion, the amount of heat energy given in that is absorbed or given out when 1 mole of a substance is burnt in air. For example, suppose if I take carbon dioxide or carbon monoxide gas and if I burn it in air, if I burn this in air, I will get carbon dioxide gas. Balance the equation. I need only one oxygen, right? Then the amount of heat energy that would be absorbed or evolved would be called as your heat of combustion. So what is heat of combustion? When 1 mole of a substance is burnt in air, the heat change that accompanies it is called as heat of combustion or standard enthalpy of combustion. Fine, do we get this in here? So I can say that the standard enthalpy changes accompanying standard enthalpy changes accompanying a reaction in which 1 mole of the substance, 1 mole of substance in its standard state is completely burnt in oxygen. Completely burnt in oxygen. Right? So that is called standard enthalpy of combustion. Right? Next, let's understand what do we mean by bond enthalpy. Right, which is also referred to as bond energy. Right, now let's consider that I have say methane gas. Right, consider methane gas. Now if I draw methane gas, you have H. There are 4 bonds that are present in this. That means when I have to break this, I would require some amount of energy to break the first. I would require some amount of energy, right, to break this bond first. Let's call this as bond first, 2, 3 and 4. There are 4 bonds of CH that have to be broken here, right? There are 4 bonds of CH that have to be broken here. So in that case, what is the average CH bond enthalpy here? The average CH bond enthalpy will be the amount of energy required to break each bond. Now, the amount of energy required to break the first the amount of energy required to break each of the CH bond is not the same. The amount of energy required to break the first CH bond is say 427, right? 427 kilojoules. The amount of energy required to break the second CH bond, because now once the first bond is gone, carbon is going to turn into a carbonium ion. It is going to turn into a positively charged ion. Hence, there will be a greater force of attraction. So the amount of energy required to break the second bond is going to be nothing but 439 kilojoules. Two hydrogens gone. The carbon is now plus 2 iron. Hence, the force of attraction of carbon ion will be more. Third bond will be even more. So the energy required to break the third bond is 452. Right? The energy required to break the last CH bond is 347. There are 4 bonds which have been broken so far. Right? So the average energy required to break this is 416 kilojoules per mole. Yes, someone wanted to ask me something?
Why last one is less?
By the time last one is there, that's only a single CH bond, there is no ion. Right? It is no longer in molecular format. Right? Okay, so that is the amount of energy. So the average energy required to convert a molecule, or the average energy required to break a bond, would be called as its bond energy. What is bond energy? In simple language, bond energy is the average energy required to break a bond. Remember, average energy required to break a bond is not equal to the energy required to break the bond. Different bonds have different amount of energies that have to be given to them to break them. Right? So the average energy that is required to break a bond would be called as your bond energy. Fine, do we get this thing clear? So the enthalpy changes required to break a particular covalent bond in 1 mole of a gaseous substance would be called as, to produce gaseous atoms or radicals, would be called as your bond enthalpy. Let's write this down, guys. Can we write the definition down? Definition. How do I explain bond energy? I can say that the enthalpy changes required to break a particular covalent bond in 1 mole of gaseous molecule to produce gaseous atoms or radicals is called bond energy. Fine. Now bond energy, one thing that you have to know about is it is always positive. Bond energy is always positive. Right? For example, I could say that suppose if I have hydrogen gas and if I split it up into hydrogen atom, then the amount of energy would be called as your bond energy. Here your delta H bond energy is set 436.4 kilojoules. That would be my bond energy, right? So what does this mean? It means that the enthalpy change in breaking the HH covalent bond in 1 mole of hydrogen gas is 436.4 kilojoules. That is the amount of energy that would be required to break a hydrogen-hydrogen covalent bond. Right? Now, this was if it was monoatomic molecule. Right? Now, for diatomic molecules, the bond enthalpy is the same as the enthalpy of atomization. Right? We have done enthalpy of atomization. If you look behind, in the previous lecture, we've done enthalpy of atomization. Right? So, for diatomic molecules, molecule, for diatomic molecule, enthalpy, bond enthalpy is the same. Again a CET question. For diatomic molecules, bond enthalpy is the same as enthalpy of atomization. Enthalpy of atomization. But for polyatomic molecules, this is not the same. For polyatomic molecules, energy required to break the bonds is different, right? That means if I have, like I showed you in the case of methane gas, if the energy required to break one CH bond is 427, and if there are 4 CH bonds, that does not mean that my total energy is going to be 427 into 4, because different bonds require different amount of energy to break. Fine, do we get this thing here? So do we understand this? What is bond energy? It is the amount of energy required, or I'll write that down also for polyatomic. For polyatomic molecules, let's consider some polyatomic molecules, say like, let's consider water. If I consider a polyatomic molecule like water, energy required to break water, there's going to be 2 OH bonds, right? The energy required to break 2 OH bonds are different, and the bond enthalpy in the case of water is bond enthalpy is 927 say kilojoules, some bond enthalpy it has, which is not twice of OH bond enthalpy. Fine, do we get this thing here? So if you have polyatomic molecules, instead of considering the amount of energy required to break the bond, you consider the average amount of energy required to break the bond, right? So if it is a diatomic molecule, then it's whatever is your bond enthalpy will remain as it is. But if it is a polyatomic molecule, instead of considering the bond energy, consider the average bond energy. Fine, do we get this thing here? Next, what do we understand by? Now so far we were doing reversible reactions. Suppose if I move on to spontaneous reaction, right? What is a spontaneous reaction? Spontaneous reaction, a reaction which occurs under a specified set of conditions, is a spontaneous reaction, right? In which the difference between the driving force and the opposing force is extremely large, right? Do we get this thing clear? So what is a spontaneous reaction? An irreversible reaction is as good as a spontaneous reaction, right? Right. Spontaneous reaction. What do we understand by a spontaneous reaction? A reaction that can occur, or that occurs, a reaction that occurs under the specified set of conditions, is a spontaneous reaction. Fine. So in other words, I can say a process that takes place on its own without any external influence can be called as a spontaneous reaction. I can say that a process that can take place in its own without any external influence is called spontaneous reaction. Fine, do we get this thing here? What is spontaneous reaction which can take place on its own, which can take place under a specified set of conditions? So such a reaction would be called as a spontaneous reaction, right? In that case, what is a non-spontaneous reaction? Non-spontaneous reaction. These are all definitions in this chapter. Now, what is a non-spontaneous reaction? A process that does not take place without continuous external force is called as a non-spontaneous reaction. So thus I can say that a non-spontaneous process cannot occur on its own. It requires external force for the process to take place. Fine. So a non-spontaneous reaction, a process that does not take place without the continuous external force is called non-spontaneous reaction. That's my non-spontaneous reaction, right? I can therefore say that a non-spontaneous reaction can be made to occur, because if I'm going to apply external force to it, I can easily determine how the reaction will occur, right? A non-spontaneous reaction will stop when the external forces or influences are stopped. A non-spontaneous reaction will stop when the external forces or influences are stopped. Right? That is your non-spontaneous reaction. Right? Let's see what are the different types of examples of spontaneous and non-spontaneous reaction. Flow of heat from hot body to cold body is naturally, and you do not have any external forces not to be given to it so that the flow takes place, and it is not in reverse direction, right? Then you can have flow of water on its own from higher level to lower level, right? Solid potassium chloride spontaneously dissolves in water, but dissolved potassium chloride does not occur on its own. Till the time I don't heat it and I don't evaporate the water, I will not get my potassium chloride crystals again. A cup of tea cools down naturally by releasing heat, but the reverse process, that is tea at room temperature, cannot absorb heat and become hot, right? Acid-base neutralization is a spontaneous process. So these are all the different types of examples that you can have of spontaneous process. All spontaneous processes proceed in one direction and cannot proceed spontaneously in the opposite direction. If you look at all the examples, if you look at all the examples that I've given you, you will see that in all of them the flow of energy is from one direction to the other direction, right? And energy in those reactions cannot flow from in the reverse direction. Fine, do we get this thing clear? So a spontaneous process may be very slow or very fast and proceeds till equilibrium is attained, right? All spontaneous processes tend to occur in the direction that will lead to equilibrium, a cup of tea cooling till the time it comes to equilibrium, heat flowing from a higher temperature to lower temperature till equilibrium occurs, right? Water flowing from a higher level to lower level till the time equilibrium occurs, right? So these are my characteristics of spontaneous reaction. Characters of spontaneous reaction. What are the characteristics of spontaneous reaction? All spontaneous reactions proceed. All spontaneous reactions proceed. All spontaneous reactions proceed in one direction. All spontaneous reactions proceed in one direction and cannot proceed simultaneously or spontaneously, and cannot proceed spontaneously in opposite direction. Right? A spontaneous process may be very slow or very fast till the time equilibrium is achieved. A spontaneous process may be very slow or fast and proceeds till equilibrium is attained. Right? All the spontaneous processes tend to occur in the direction. All spontaneous processes tend to occur in a direction that will lead to equilibrium. That will lead to equilibrium, right? This is also called as your second law of thermodynamics. So your spontaneous reactions follow second law of thermodynamics, right? Okay, we'll stop this here for the day. Thank you very much.